Hey everybody, this is Dr. A, and in this video we are going to be exploring another example of right triangle trigonometry. So remember, whenever you are practicing these problems and you're watching these videos, the best way to learn is to write everything out. You need to get something to write with, some paper or pencil, and you need to work the problem along with me. Of course, you can pause the video as you need, but you cannot just watch this. Remember, math is not a spectator sport. You have to participate. So let's go ahead and get started. On the given information, we are told to compute the sine, cosine, and tangent of an angle theta. And the right triangle that you are given is being drawn right now. Not my best artwork. So this is the right angle here. And then the angle theta you're interested in is up here. The height of this right triangle is given to us as 1 meter, and the length of this right triangle is given to us as 1.5 meters, okay? And so again, this is all of our given information. So you want to write this down, and now we are ready to attack the solution to this problem. So one way you can approach this is you can go back to the basic definition of sine, cosine, and tangent, okay? So ask yourself, what is the basic definition of sine, cosine, and tangent for a right triangle? Okay, well, if you remember, the sine of an interior angle in a right triangle is equal to the opposite side divided by the hypotenuse. Okay, and then the cosine of an interior angle of a right triangle, in this case cosine theta, is going to be equal to the adjacent side divided by the hypotenuse length. And then the tangent of an interior angle is equal to the opposite side divided by the adjacent side of that right triangle. And again, this is right triangle trigonometry. So your triangle that you're dealing with needs to be a right triangle specifically. It can't be, any other kind of triangle. It has to be specifically a right triangle, and one of those three angles needs to be 90 degrees. So these are the basic definitions. And when in doubt, you can always go back to these three very basic definitions, okay? Now, if you look carefully at this figure, you'll notice that we don't have the hypotenuse length just yet. So let's go ahead and write that in here. Let's say that this diagonal length right here, this is our hypotenuse, and let's call it R. And of course, we don't have that right now, but we can get it. And in fact, we have to get it right now in order to make these computations happen. So let's go ahead and get that hypotenuse length, and I'm going to go ahead and make sure we're clear on this. R is equal to the hypotenuse of this right triangle, okay? And of course, you remember that you can use the Pythagorean theorem to calculate the length of a hypotenuse for a right triangle. And so that's going to be the square root of what? Well, it's the square root of one of the sides squared plus the other side squared, all right? So we're going to say that's the square root of 1.5 meters squared plus 1 meter squared. And remember, if you look carefully, this triangle has units. It has measurements of meters. So it's very appropriate to include the units of measurement of meters inside of this calculation. So let's go ahead and let us use a calculator to help us with this. So 1.5 squared, of course, is 2.25, okay? And then 1 squared is still 1, so this kind of breaks down to 2.25 meters squared plus 1 meter squared. And then you add those numbers together, and you'll have the square root of what? 3.25 meters squared. And if you remember your basic algebra, you can break this square root up as 3.25 times the square root of meters squared, just to help us track our units. And so when you take the square root of 3.25, that number becomes about 1.803. And then, of course, the square root of meters squared is just left with meters. So I encourage you to embed those units into your calculations so you have a full understanding of what's happening with these unit combinations and manipulations. And of course, this is a length, right? This is the hypotenuse is a physical length, so it makes sense that it has units of length, which are meters in this problem, okay? Well, now we're ready to move forward and actually compute what the problem asked us to compute, the sine, cosine, and tangent of that angle theta, okay? So we can say the sine of theta is equal to what? Well, what is the side that is opposite of angle theta? That's 1.5 meters. So we're going to say sine of theta is equal to 1.5 meters divided by the hypotenuse length, which was 1.803 meters. And if we perform that calculation, we get 0.832. Now, ask yourself this, does this 0.832, does it have units of meters here? The answer is no. Why is that? Well, if you notice, the meters cancel. You have meters in the numerator and meters in the denominator that cancel themselves out. So the sine of theta, when you calculate this 0.832, it is unitless here, okay? Now, in a similar way, we can use the definition of cosine of theta, which is the adjacent side over hypotenuse. What is the side that is adjacent to angle theta? Well, that's the side next to it that is not the hypotenuse. So that would be 1 meter. And so we're going to say cosine of theta is 1 meter divided by the hypotenuse length, 1.803 meters. And let's see what we get on for that calculation, 1.803. And I calculate this to be 0.555. And of course, the units of meters cancel here. And then our last calculation is tangent of theta, which is defined as the opposite side over the adjacent side. So what is the side opposite of theta? It's 1.5 meters divided by the adjacent side, which is 1 meter. Opposite over adjacent. So you get 1.5 meters over 1 meter. And of course, this is just equal to 1.5, and my units of meters cancel. So these are our answers right here. These are our 3 answers, okay? So that summarizes this example. I hope you learned a lot from it. Go ahead and hit like and subscribe, and we'll see you next time.